The title of my presentation is Computational Welding Mechanics-Based Approach for the Optimization of Process Parameter in Laser Welding of Inconel 792 Nickel-Based Alloy. I want to start with a brief outline, brief summary. I will start with the introduction and motivation. Then I will go ahead with the description of the numerical model that we developed. Then I will go ahead with the result and discussion, and as always, the conclusions. In reality, this is the first part of a bigger project, 2 years project called Laser Welding and Repair of Superalloys that is founded by the European Union, and in particular by the Italian Ministry of Research and Universities. The topic of this project is to study the weldability and repairability of some grades of nickel-based alloys, in particular the Inconel 792, because its poor weldability and repairability, always in the frame of sustainability and the sustainability perspective. So in this project, the first part was to develop a numerical model. The result I'm going to show you in this presentation. And with this numerical model, we can predict residual stresses and thermal stresses that would allow us to guide the next decision for the trials. The main problem of such kind of alloys is the cracks formation during welding. The composition of the alloy is given in this table. Is the Inconel 792. It is a nickel-based alloy with a great amount of chromium, cobalt, and the numerical model is schematized in this picture. In particular, you can see the mesh of the plates. We exploit the symmetry of load and geometry, so we modeled only 1/2 of the plate with 8-node brick finity elements. The mesh, as always, is graduated close to and finer close to the welding line in order to capture the high thermal gradients that arise during laser welding. The thickness is 2 millimeters, as in the experiment. And we applied the standards boundaries condition for the simulation, in particular thermal boundary condition, convective and radiative heat loss. The mechanical condition were isostatic, and all material properties were taken as a function of temperature. The strain hardening model was a kinematic strain hardening model. The fusion zone is simulated as well in the mechanical computation by dilating the thermal histories at nodes that overcome the melting temperature. Finally, we try to investigate, the goal of this first part of the project. We try to investigate the influence, using this model, the influence of some parameters on the residual stresses and thermal stresses. In particular, we try to investigate the influence of the preheating temperature. It is a very important parameter, but also the influence of power, laser power, and the welding speed. In order to obtain the correct shape of the fusion zone, we use a combination of 2 conical shape heat sources with the Gaussian power density distribution. The 2 functions combined together are shown in this picture. Capital Q1 and capital Q2 are the Gaussian power density distribution, classical conical shape heat sources that we can find in literature, but in this work are combined together. And the combination is schematized in the figure here at the bottom left. using this combination of the two sources, we are able to obtain the correct shape of the fusion zone, as you can see in this picture at your left, in which we can see the match between the numerical result, the colored red zone here, and the experimental result. It is given as a cross section of the bead. In this table, you can see the calibrated parameter of the source that we have obtained by numerical simulation, by matching the experimental and numerical results. About result and discussion, I want to start with the result of thermal results. In particular, we try to investigate two conditions. The first one is the condition at constant power and speed, and by increasing, of course, the preheating temperature, sorry. And the second condition is the influence of preheating temperature by keeping constant the weld put width. In this case, if we want to obtain a constant weld put width, we need to reduce the power, the laser power, as the preheating temperature increases. And we found a linear variation of the power given in the equation here below, where P is the power, PHT is the preheating temperature, and capital A and capital B are two parameters calculated by numerical result, by numerical trials. So about the influence of the preheating temperature on residual stress, here you can see only the longitudinal component because it is, as you know, the measure component in butt welded joints. In the two conditions, and at the top, you can see the condition at constant power and speed by increasing, of course, the preheating temperature. And in the figure at the bottom, the condition at constant weld put width. In both cases, we obtain a reduction, of course, of residual stresses as expected as the preheating temperature increase. But more significant reduction are obtained in the first condition at constant power and speed. In particular, again, we can see that if we want to have a significant reduction of residual stresses, we need to operate with a preheating temperature over 500 degrees or even 600 degrees. And this is a result that more or less was found in agreement with some other results found in literature about arc welding, not laser welding, but arc welding of such kind of alloys. About the effect of welding speed on residual stress, here the result using a preheating temperature of 400 degrees, we obtained that both at the low and high power laser power, by reducing the welding speed from 25 millimeter per second to 5 millimeter per second, we have a reduction in both cases of the residual stresses. But the greatest reduction was obtained by the combination of high power laser power and low welding speed, as you can see by the arrow here in this picture. About the effect of welding speed on crack susceptible zone, the crack susceptible zone is the zone in between the solidus and liquidus temperatures, and where during solidification we have a sort of mushy zone where it is expected to find cracks, hot cracking, or cracks. So it is important to understand how the welding speed can influence the extension of such a crack susceptible zone. And we investigate these effects by using a welding speed of 5 millimeter per second and 55 millimeter per second. And we obtained that using a low welding speed, 5 millimeter per second, the crack susceptible zone extension is reduced, but the thermal stresses increases, above all in the subsolidus zone. Vice versa, using a higher welding speed, 25 millimeter per second, we found that the crack susceptible zone extension is increased, but the thermal stress decreases. So the influence of welding speed on cracking, solidification cracking, is controversial. Also in literature, we found that this effect is controversial also in literature. We carried out some preliminary experimental results, some trials using different combinations of the laser power and welding speed. You can see in the graph at your left the different combination we tried right now, using a preheating of 300 degree and 400 degree, and thickness of the plate 3 millimeter and 2 millimeters. In all the trials, we were not able to obtain sound welds, in the sense that in all trials we found transversal cracks that you can see, for instance, in the central figures of this slide. And we suppose it is a problem due to the embrittlement temperature intervals that characterized this alloy, and that you can see in the graph on your right, where I've plotted the elongation of the rupture as a function of temperature. This phenomenon, which goes by the name of strain age cracking. So for the conclusion, we can say that such kind of alloy, nickel-based alloy, Inconel 792, is very difficult to weld. Or in other words, it has a very low weldability, at least in the equiaxed form and by laser. According to the simulation and literature, if we hope to obtain sound weld, probably we need to use or to operate with preheating temperature over 500 degrees. But unfortunately, it is very difficult to apply in laser welding. It is difficult to operate at so high preheating temperature. So another possibility that we will be explored in the next future is to use a second laser or arc source in order to preheat or post-heat the weld bead. As I told you before, the effect of welding speed is controversial. Lower welding speed reduce the crack susceptible zone extension, but increase the thermal stresses, and vice versa for higher welding speed. The next step is to better investigate the nature of cracks that we observe in all our trials by using EBSD and SEM analysis, because we need to understand if we have to do with solidification cracking or sub-solidus weld cracking. Once we have understood this problem, we can postulate other mitigating action to try to obtain sound welds, that is, welds without cracking. Okay, that's all for now. Thank you very much for your attention.